De Morgan's laws were encountered in the idea of set theory, or within set theory, and they have an analogous meaning in logic. It turns out that set theory and logic have a lot of parallels. For example, the and is a lot like intersection, the or is a lot like union. Let's take the statement, it is not true that you'll get an ice cream cone and $1 million. Now, if it's not true that you get an ice cream cone and $1 million, then what can you say? Well, for that not to be true, you got to get no ice cream cone or you get no $1 million. Of course, you don't get either. That's just fine. That makes the statement untrue. So the symbolic representation of this statement is not P and Q, where P is you get an ice cream cone and Q is you get $1 million. This is saying it's not true that that compound statement is true. The equivalent statement is you won't get the ice cream or you won't get the million. Not P or not Q, as we symbolize here. So we're saying that not P and Q is the same as not P or not Q. Now let's verify that using a truth table. If we have P and Q, we can write the truth values as we've done now. Then to evaluate not P and Q, well, first we'd better evaluate P and Q. Then we can evaluate not P and Q. Having evaluated not P and Q, we can evaluate not P or not Q. Well, first we evaluate not P, we evaluate not Q, then we evaluate not P or not Q. To evaluate P and Q, we just look at the P and Q columns and see where they're both false. See that they're not both false in any other column or any other row, so that we have these truth values for P and Q. For not P and Q, well, we just reverse the truth values for P and Q. If it's P and Q is true, then not P and Q is false. And if P and Q is false, then not P and Q is true. Okay, not P. What about not P? Well, we look back at the P column and reverse its truth values. True becomes false, and false becomes true. Not Q, same thing. True becomes false, false becomes true, true becomes false, false becomes true. Now how do we evaluate not P or not Q? We look at the not P and the not Q columns and connect them with the disjunction with the or, which means that when they're both false, not P or not Q has to be false. Otherwise, not P or not Q has to be true. And I made a real bad boo-boo over here. Let's fix that. Okay, now what did I do over here that you probably raised your eyebrows at and questioned? I did the P and Q as if it was a disjunction, didn't I? Okay, I made a terrible mistake here. Said when these are both false, this will be false, otherwise they're true, and that's not the case. The conjunction P and Q is true when P is true and Q is true, otherwise it's false. So we've got an error here, and now hopefully we fixed it, and hopefully you didn't get too confused by that. If you did, I hope that you're less confused now, because the and clearly means both conditions have to be true. I wrote that down without thinking, and I did that accidentally. It wasn't on purpose. I'm not going to re-edit this. I'm going to leave this in here because you'll see that I can do it and so can you. You've got to check things out very carefully and go back over your problem to make sure you've done it right. Now, what's that going to affect? Well, that's going to affect the next line, the not P and Q, and the true is going to become false, of course, and all the falses become true. So now hopefully we've corrected this, and hopefully you believe me. What we're trying to compare is the not P and Q with the not P or not Q. That is, we're trying to compare the truth values here with the truth values here. And we see that these columns are identical. They have identical truth values, which means that these statements have exactly the same meaning in all cases. They have the same truth value in all cases, so that they have the same meaning. And this verifies De Morgan's law for the AND case, for negating the AND. Now, if we have the other case where we negate the OR, what do? Well, we take, for example, the statement, it's not true that you'll get an ice cream cone or $1 million, symbolically represented by not P or Q. And we're going to say that the negation of that, if it's not true that you get an ice cream cone or $1 million, then you're not getting either. You're not getting the ice cream cone and you're not getting $1 million. So that the not P or Q statement would be translated as not P and not Q. And we can set up truth tables again. We're trying to evaluate the not P or Q, so we first evaluate P or Q, then we evaluate its negation. Then we evaluate the not P and the not Q, so that we can evaluate the not P and not Q. Now we'll quickly write down the truth values here. And then we'll do this carefully. The OR will have a false where these are both false, and otherwise it'll be true, the way I said about the AND a minute ago, which wasn't the case. Okay, that's the OR. So when we negate these values to get these values, we're going to change them all as indicated. Then we negate the P's just as we did before. True, true, false, false becomes false, false, true, true. True, false becomes false, true, false, true. Now, not P and not Q, we put these together with an AND. Only true if they're both true, which happens down here. Otherwise, false. Then we compare the not P or Q column with the not P and not Q column. And where I wrote false here, I meant to write true. I said true. True and true gives us true. And we see that the columns match. Now you try to do that yourself, and try to do it without making the mistakes that I did.